Hello everyone, today we are doing section 4.2, polar equations and graphs. We do have graphs in Cartesian coordinates. In Cartesian coordinates, graphs are looking like this. Y equals f of x, right? Y is dependent variable, x is independent, and there is a function. Function can be something like squaring function, square root, sine, cosine. In polar coordinates, graphs are going to look like r equals f of theta. Here theta is going to be independent variable and r is going to be dependent variable. Again, we have two pairs of numbers for graphs in Cartesian coordinates and two pairs of numbers for graphs in polar coordinates. Let's talk a little bit about graphing in Cartesian coordinates versus polar coordinates. In Cartesian coordinates, grid lines are lines of constant x and constant y. So x equals constant, mean that x equals 1 or x equals 2, something like this, and y equals constant. We're going to create something like a graph paper for Cartesian coordinates. What does it mean? In Cartesian coordinates, I'm going to graph lines x equals constant. They're going to produce vertical lines like 1, 2, 3, 4, and horizontal lines. It's gonna look like squared paper, right? If somebody gives you a point x and y, you can just look intersection of which x and which y is this. For example, the point 3, 2, you look, okay, where is x equals 3 over here, where y equals 2 over here, so the point comes over here. This is kind of graph paper in Cartesian coordinates. How graph paper in polar coordinates is going to look? Well, similar to Cartesian coordinates, we are going to set up theta equals constant. For example, can be 30 degrees or 90 degrees or something like this, and r equals constant. Can be r equals 1 or r equals 2 or so on. How these curves are going to look? Well, I'm going to draw normal Cartesian coordinates, but I'll try to graph some lines of theta equals constant. Well, theta equals 30 degrees is going to produce a line looking like this, right? Remember that in polar coordinates, when r is negative, we're going to have points on complementary side of that line. And 90 degrees is going to produce a line like this, and all other angles are going to produce some lines which will go through the origin. These are lines of theta equals constant. R equals constant are going to produce circles of radius 1, for example, radius 2, and so on. So this is graph paper for polar coordinates. Now somebody gives you a pair of points like r equals 2 and theta equals 30 degrees, and you're just going to find out, okay, where is my radius equals 2 and where is my theta equals 30 degrees? The point is going to come over here, same as Cartesian. Normally, we're not going to use special paper to graph it, because usually, well, if this paper is like square paper, this paper just like you have to print it out. So we're just going to measure angles if we need to measure them. Okay, let's try to graph some simple lines in polar coordinates. Let me erase this stuff. We're going to start with example 1. And that's going to be r equals 3. Well, we already know that r equals constant is going to produce a circle. In this case, we are going to have a circle of radius 3. Radius 3 means that it goes to 3 over here and 3 over here, right? Example 2, let's graph theta equals 30 degrees. We are going to have a line, and there's 30 degrees over here, plus a complementary side of this is going to be, these points over here are going to be negative r's. So this is a line and this is a circle. Example number 3, I'll try to graph something a little bit more complicated. R equals 2 sine of theta. Well, that's a function already, right? sine is a function of theta and dependent variable is r. What I'm going to do, I'm going to build a little table to graph it first time, and then I'm going to explain how we graph it without doing table. I'm going to put independent variable theta over here and dependent variable r over here. I'm going to consider several angles: 0 degrees, 30 degrees, 90 degrees, 120, and 180 degrees. So just 5 points. Okay, how I'm going to kind of calculate everything? Well, like normally when you plug in x, you get y, right? Here we plug in theta, we get r. I'm going to plug in 0, sine of 0 is equal to 0, so my first r is 0. Sine of 30 degrees equals 1/2 of table value, right? 1/2 by 2 is going to give me 1. Sine of 90 degrees is going to be 1, multiplied by 2 is 2. Sine of 120 degrees is going to be same as sine of 30 degrees, right? And we are going to get 1 again. Oh no, that's not 120, 150 is going to give us 1. 120 is going to give us actually a square root of 3 over 2, right? Because it's like 60 degrees angle. And we multiply it by 2, so it's going to be a square root of 3. And 180 degrees sine again is going to be equal to 0. Now I'm going to use these points to graph. Well, I'm drawing Cartesian system of coordinates just to kind of get some position on the plane, but normally you can just draw polar axis and start graphing it. So at 0 degrees, the radius is 0, so the point sits over here. At 30 degrees, about, well, around 30 degrees, we're going to have actually 1 unit, right? And then at 90 degrees, we have 2 units. Let's imagine it's going to be over here, 120 degrees, somewhere here. We're going to have a square root of 3, a little bit less than 1, and by 180 degrees we are going to return back to 0. Well, looks like 4 points. I'm going to draw actually a smooth curve through these points, which is going to look very much like a circle. Is it actually a circle? Can we kind of verify it without doing like many points over here, just to check if they're actually making a circle? Yeah. I'm going to show you how to verify that this equation actually is going to be a circle. So what I'm going to do, I'm going to raise my table and do equation. Everyone remembers how equation of a circle looks, right? Circle, it's x minus x0 squared plus y minus y0 squared equals radius squared, right? x0 and y0 are center of a circle, and this is radius of a circle. This is circle not centered at origin. What I'm going to do to this equation, I'm going to multiply both sides of this equation by r. So it's r by r here, and 2 sine of theta by r over here. This is r square, and I remember that r square equals x square plus y square from Cartesian coordinates. Remember transformation of Cartesian to polar and polar to Cartesian. What is r sine of theta? It's actually y coordinate, so I have 2y here. And my equation is going to look like a Cartesian equation: x squared plus y squared equals 2y. It does not look like a circle equation. I'm going to modify it a little bit by completing the square and turning it into circle equation. So what I'm going to do, I'm going to move 2y to the left side of my equation and going to write it down like this. Now I see that if I want to have over here a perfect square, I'll need to add 1 over here, and to not change my equation, subtract it at the same time. So now 3 terms like y squared minus 2y plus 1 are going to give me y minus 1 perfect square. This minus 1 is going to be just minus 1 equals 0. Still does not look like equation of a circle. I'm going to move minus 1 to the right side, and my equation is going to look like this. Now it looks like equation of a circle, right? The radius of this circle equals to 1, and the center of this circle happens at point 0, 1. And I'm going to graph this circle. And you can compare the previous picture, which I raised already, with my new picture of a real circle, which equation is describing. So center 0, 1. Well, 1 unit in y direction, 0 unit in x directions, and radius 1. And that's going to be exactly the circle I was graphing before, right? So equation is describing a circle. Now, what I want you to do, guys, I'm going to give you another equation, and I want you to try it on your own without my help. And then I'm going to show you my solution. So my next equation is example number 4, and that's going to be r equals 6 cosine of theta. Similar to the previous one, but instead of sine I have a cosine. Let's see how the circle is going to be different. So you try it on your own. I'm going to count to 5 and solve it. Okay? So 1, 2, 3, 4, 5. You can start video again. I'm going to apply the same technique I was using for sine. I'm going to multiply by r both sides of this equation. I'm going to write down that this one is x squared plus y squared. What is this? Well, this one is x, right? Remember that r cosine of theta actually is x in Cartesian coordinates. Now I'm going to move x together, and on the left side is 0, right side is 0. Here I'm going to complete the square. To complete the square here, I'm going to look at 6, and 6 is like 2, the square term over here, right? So 2 square terms, 2 is going to be like, the term is going to be 3, right? That's like 2b, so b is going to be equal 3. So it's going to be x squared minus 6x. If b is equal to 3, means that I'll need to add 9 here to complete the square. To not change my equation, I'm going to subtract 9 right away, and that's going to make complete square, x minus 3, and you can just check it by opening this complete square. I'm going to put this minus 9 over here, so I don't have to copy equation second time. And what I see, I have a circle with center 3, 0, and radius 3. Remember that this is radius square. Let's graph this circle. So 3 units in x direction, and the radius is 3. You see, my both circles are coming through the origin. Well, my second circle is not looking very nice. What we also see, guys, circles with cosines are going to be like horizontal circles. They're going to have a center on x-axis, and they can be moved to this direction or to this direction, but they always going to go through 0 to origin. Circles with sine are going to be vertical circles. Okay, so let's move to my next example. Let me erase example number 4. Next curve is not going to be a circle. It's called cardioid because it looks like a heart. Example number 5, cardioid. How equation of cardioid look? Well, can look like this. 1 minus sine of theta. I'm going to do, guys, for cardioid, we're building a table of 5 points. I'm going to use special thetas here. Watch which thetas we're supposed to use when we deal with cardioids. So thetas are 0, pi over 2 pi, 3 pi over 2, and 2 pi. I'm going to plug them into the equation, calculate r. I'm going to start with 0. Sine of 0 is 0, so r is going to be equal to 1. Pi over 2 is going to give me 1, 1 minus 1 is 0. Pi here is going to give me 0 again, and 1 minus 0 is 1. 3 pi over 2 is going to give me minus 1, minus is plus, and plus 1 is 2. And 2 pi is going to return me back to original, to 1. How the graph is going to look? Well, I'm going to graph the points, and then you just need to see how to shape actually curve in these points. So theta equals 0, r equals 1. 0 is sitting over here, r equals 1. Well, let's imagine that's 1 unit, okay? Theta equals pi over 2 of vertical line, and radius is 0. I'm going to graph it as point over here. Theta equals pi, this side of the line, it's again 1. Well, this one means distance from the origin to the point. Does not mean that it's going to be the number over here. 3 pi over 2 is going to give me 2 units. So this one is going to return me back to this point and give me 1 again. Now, what I have actually 1, 2, 3, 4 points. You can build anything through these 4 points, right? That's the best is going to be a triangle. But I'm going to connect it with a smooth line because I do identify that the equation is the equation of a cardioid. And get a little hard over here. Unfortunately, if you wish to really get the cardioid by points, it's going to take too long. Now, what I want you to do, guys, I want you to graph on your own cardioid 2 plus 2 cosine of theta. I'm going to, you can stop the video and I can count to 5 and give you solution, and then you can compare your solution to mine. Okay, 1, 2, 3, 4, 5. So I'm going to start with the table, theta r. I'm going to do very same points. 0, pi over 2, pi, 3 pi over 2, and I'm not gonna even do the 2 pi because I know they're gonna give me the same number as 0. At 0, cosine is equal to 1, so 2 plus 2 is 4. Pi over 2, cosine is 0, so it's 2. At pi, cosine is negative 1, so it's negative 2 plus 2 is 0. And 3 pi over 2, cosine is 0, and we're going to get 2 again. Well, again, I'm going to get just 4 points, but I know that it's a cardioid, so I know how to connect them. So, at 0, theta equals 0, the point is 4. Theta equals pi over 2, the point is 2. Pi is 0, and 3 pi over 2, again 2. So, 4 points. Now I'm going to connect them into a nice heart shape. So that's my cardioid. You see that cardioid with sine was kind of vertical, cardioid with cosine is horizontal. Also, you can see that minus over here is moving cardioid down, and plus over here is moving cardioid in positive direction of x-axis. Okay, next curve is going to be a rose. A little bit more complicated, but that's going to be our last example for today. So, example number 6, rose. Well, equation is going to look like this. 2 cosine of 2 theta. And in general, it can look like r equals, well, some number over here, amplitude, and cosine of n theta. Here, number can be changing, not necessarily supposed to be equal to this number too, so it can be, this is independent number, this is independent number. This number is going to be a natural number, so it can be 2, 3, 4, 5. Okay, how do I build the rows? Well, again, because I do know that's going to be a rows, I'm not going to build lots of points. And I remember that when we multiply theta by 2, we are kind of making a period of this cosine twice shorter, because remember, period is 2 pi over omega, right? So here period is going to be just pi. So what I'm going to do, I'm going to make a shorter table, theta over here and r over here, and that's going to be 0, pi over 4. I'm making a shorter table from 0 to pi, not from 0 to 2 pi, 3 pi over 4, and I'm going to do pi here, but generally it's not going to be necessary. So what is going to happen at 0? Plug in 0 here, cosine of 0 is equal to 1, so it's 2. Pi over 4, plug in pi over 4, multiply by 2, get pi over 2, cosine of pi over 2 is 0. Pi over 2 is going to give me 2 by pi over 2, just pi, cosine of pi is negative 1, so I'm going to get negative 2. And 3 pi over 4 is going to give me, multiplied by 2, 3 pi over 2, and cosine of 3 pi over 2 is 0 again. And pi is going to give me, again, 2, just because that's going to be like 2 pi here, and cosine of 2 pi is equal to 1. Now, I'm going to graph the points and explain how do I draw the curve after that. So at 0, I have 2. 1, 2. Pi over 4, line over here, is going to give me 0, so it's over here. Then pi over 2. Pi over 2 is this vertical line, right? But because I have negative r, I'm going to actually graph my point over here on a negative complementary ray over here. Next one is 3 pi over 4. 3 pi over 4 is going to be something over here. And I get 0 again. And next one is pi. And I'm going to get, let me see, I'm going to get 2. 1, 2. Now, what I'm going to build using these points? Well, please watch how I do this. So I start at 2, and my curve will go slowly to 0, right? After that, from 0 we'll go to my point -2. From -2 it will return to 0. From 0 it's going to go to 2. And that's almost the whole flower. I'm going to repeat the other lines. What we have is called a rose with 4 petals. These are petals. How do we know how many petals the rose is going to have? You take the number n, multiply by 2 if n is even, then 2n petals. If n is odd, like 3, 5, 7, it's just going to be n petals. Usually, what you will need to know for graphing petals, you will need to know how many petals, you will need to know how bigger petals. So this 2 and this -2 and 2 are showing how far away actually the vertex of the petal is going to be from the origin. And you just need to kind of use a symmetry. You know that all these roses are always going to be symmetrical. So I'll ask you to graph a rose, and that's going to be like odd number of petals. And I think that's going to be all for today's class. So let me maybe erase this up. So a little self problem for which you can stop your video, and I'm going to count to 5 and you can start it again. So self work. R equals sine of 3 theta. Because 3 is odd, we are going to have 3 petals. Okay, so you can stop your video and try to graph it yourself. Well, try to guess what points you will need. And I'm going to count to 5 and show you solution. So 1, 2, 3, 4, 5. Okay, I'm not gonna do the table for this one. I'm going to just find out, well, first, at which theta the maximum is going to happen. I know that maximum of sine is equal either 1 or -1. And second, I know that there are 3 petals, so I'm just going to see that the length of each petal is going to be, the vertex is going to be 1 unit away from the origin, because maximum value for the sine is equal to 1. So I'm going to start by setting up sine of 3 theta equals to 1. That's like maximum value. So what can I say about 3 theta? 3 theta equals pi over 2, right? Pi over 2 is going to be our first angle, and from where theta is going to be equal pi over 6. So I found my first petal. I know that there are 3 of them and they're on equal distance from each other. So I'm going to graph line pi over 6 and vertex of my petal. And where are going to be other petals? Well, imagine that you will need to divide 2 pi into 3 parts. 2 pi over 3. And that's going to be like how far away each petal is going to be from each other. Right? You know that this one is already like pi over 6. It's pi over 6. So what is going to be the next one? The next one is going to be pi over 6 plus pi over 3. Let's multiply this by 2, so it's 4 pi plus pi over 6, which is 5 pi over 6. I'm going to graph 5 pi over 6 and 1 unit in this direction. This is much further away, I guess. And if I add to 5 pi over 6 another 2 pi over 3, just to get the third one, I'm going to get what? Multiplied by 2, it's 4 plus 5, it's 9 pi over 3, or 3 pi over 2. 3 pi over 2 is over here, so I'm going to just graph 1 unit here. Trying to graph too many. 1 unit. Now I'm just going to draw my petals. And if you do same, no one is gonna complain, actually. Okay, so what do you need to know from this class? It's very hard to memorize all the curves. I want you to know how to graph circles and how to graph cardioids. You don't need to memorize how to graph roses, but in the homework you can always refer to the book and just look how they do the roses. Okay? For like how many petals, maybe you will need to know how many petals. So odd numbers, same amount of petals, even number multiplied by 2. Okay, well, that's all for this lecture. And do your homework. If you have any questions, email me and ask. Okay. Thank you.